Hi, my name is Kavisha Selvam, student ID RA24041 from Group 2 in section RA11. And today I'll be presenting Group 2's work-based project for Fluid Mechanics code DRA1713. Group 2 has chosen the dam system as its real application of fluid mechanics system. First, I'll be introducing the team members for Group 2. We have Chanzi Ni RA24035, myself, Kavisha Selvam RA24041, Agnes Kwek Zixin RA24064, and Iskandar bin Darajatun RA24072. Next, I'll be presenting the introduction for this work-based project. A water dam system is a barrier that creates a reservoir by stopping, slowing down, or restricting the flow of surface water or underground streams. A dam system can also be used to collect or store water which can be evenly distributed between locations. Dams generally serve the primary purpose of retaining water, while other structures such as the floodgates or levees are used to manage or prevent water flow into specific land regions. Dams are used for flood control, water supply, and hydroelectric power generation. Reservoirs created by dams not only suppress floods but also provide water for activities such as irrigation, human consumption, industrial use, aquaculture, and navigability. Moreover, a dam generally consists of an upstream slope and a downstream slope. A dam is made up of many components such as the crest, the heel, the toe, the parapet walls, the gallery, the spillway, the abutments, the sluiceway, the freeport, the dead storage level, and the diversion tunnel. Conversely, fluid mechanics is the study of forces and flow within fluids. Fluid mechanics can be divided into three branches, which are fluid statics, kinematics, and fluid dynamics. The water dam system is a real application of fluid mechanics and is considered as a fluid mechanics system. Application of fluid mechanics theories in the dam system includes Bernoulli's equation, flow patterns, Darcy's equation, Reynolds number, loss coefficients, and resistance coefficients. Bernoulli's equation accounts for the changes in elevation head, pressure head, and velocity head between 2 points in a fluid flow system. Flow patterns is the understanding of different pattern flows, such as laminar flow and turbulent flow, where it's essential for predicting pressure drops and overall system performance. Darcy's equation is used to calculate the pressure drop in pipes due to friction. Reynolds number helps to determine whether the flow is laminar flow or turbulent flow, which influences the choice of pipe diameter and pipe material. Loss coefficients is to determine the losses for valves and fittings, which aids in the selection of appropriate components to minimize energy losses. Last but not least, resistance coefficients is the constant proportionality between the energy losses and velocity head when it flows through an enlargement or contraction of the flow section, around an elbow, or through a valve. Moving on, next is the objectives of this book-based project. There are a total of 6 objectives. The first is understanding the fluid mechanics principles. To comprehend the fundamental and basic principles of fluid mechanics, including the behavior of fluids in response to force and pressure, and its application in continuum mechanics. Second, identifying the parameters and characteristics of the dam system. To recognize the parameters and characteristics of the dam system, which ensures a calculated and thorough designing process and a guide for brainstorming improvements for existing dams. Third, calculating the flow of the dam system. To determine the value of pressure, velocity, volume of flow rate, total major loss, total minor loss, and the type of flow pattern in the system which takes for it to run and function. Fourth, examining the losses that may occur in the dam system. To analyze the losses that may occur in the dam system, which includes minor loss, major loss, structural loss, and operational loss, so that ideal efficiency can be achieved by the system. Fifth, identifying ways to reduce the energy losses in the dam system. To propose ways to reduce the energy losses in the dam system, which helps to contribute to the Sustainability Development Goals (SDG) by UNICEF, including SDG 6 (Clean Water and Sanitation), SDG 7 (Affordable and Clean Energy), and SDG 9 industry, innovation, and infrastructure. Last but not least, the sixth objective is practical applications in engineering field to relate acquired knowledge with real-world engineering applications, which emphasizes the significance of fluid mechanics theories in designing, operating, and optimizing piping systems across various industries. That is all from me. Thank you.
Selamat sejahtera. My name is Iskandar and my ID is RA24072. So today I will explain the characteristic of a dam system. So for the first one is the penstock. Penstock, it functions to channel water from high pressure to turbines. So for our penstock, we use steel as its material because it possesses high strength and it is often used in high pressure conditions. So for the foundation, we use granite bedrock. So its advantages is its resistance to earthquakes. It possesses rigid and dense structure, make it less susceptible to deformation or cracking. It also has high strength. It capable of withstanding the immense pressure exerted by the dam and water. For our turbine, we use Kaplan turbine. It is a device that converts energy from a moving fluid such as water, steam, gas, or air into mechanical energy, which is typically used to drive generators for electricity production. So what is the advantage? It has high energy conversion efficiency. It is the most efficient types of turbines, achieving efficiencies as high as 90 to 95%. It is also suitable for high flow rate and capable of handling large volumes of water. For generator, we use permanent magnet generators. So what is generator? Generator functions to convert mechanical energy into electrical energy through the process of electromagnetic induction. So what is the advantages of permanent magnet generators? It does not use or require external excitation systems like slip rings, and hence it reduces the energy loss. And for our wall, it mainly responsible to store water from reservoir before it is released as it reaches its capacity. The characteristic of our wall, we use 120-meter long, 50-meter thickness at the base, 20-meter thickness at the top, and it has a highness of 130-meter deep. Our wall also has the shape of arch because it is highly effective in withstanding the immense pressure exerted by water while using less materials. So the advantages is it is able to withstand the water pressure, and the shape is also inherently strong since it distributes the force. The curvature also allow it to fit in the mountain belt. Our dam also has intake tower. So intake tower responsible for controlling and directing the water from a reservoir into the penstock, which delivers water to the turbines while ensuring proper flow of water for energy generation. So what is the characteristic? It is connected to penstock to allow water to flow through the penstock. We also has generator turbine house. So this house allows the turbine and generator of hydroelectric system and ensure the conversion of mechanical energy from turbines into electrical energy. So for our house, we use reinforced concrete to withstand the seismic activity to allow the building to maintain its structural integrity.
Hi, my name is Agnes Quek and my ID number is RA24064. Today I'm going to present about the AutoCAD of sketches and the calculation. First, we can see we got a plan view here. Our dam are designed in a small river between the mountain, and we designed the hole that the water in is deep under the water about 8.25 meter, and it have a slope to the horizontal pipe with a 27 degree. We got two elbows and at the end of the pipe to decrease the height between the pipe to the land, and we can have a generator turbine house behind the dam to generate electricity. The wall of the dam we designed as narrow at the top and wide at the below because the gauge pressure under the water will increase proportional with the depth of water according to the depth of water. So we've got a 2 meter at the top of the dam and 5 meter at the bottom of the dam to hold on the pressure. And we also designed a tower for the dam for a purpose of observing the dam. And we designed the scale is 1 meter to 1000 millimeter in the AutoCAD. Next, we can see this is a plan view of the dam, and we can see the generator turbine house is built at the lower left of the dam because we assume that they have a flat platform for building to build among the mountain. We can see this is the plan view of the dam, which is the front view of the dam, and the hole of water in is at the 8.25 meter from the surface water, and the beside of the dam is the mountain, and we got the dam height is 30 meter and the width of the dam is 12 meter. Next is our calculation. The first question is the pressure at the base of the dam, and we use the gauge pressure equation to solve it and assume that the atmospheric pressure is 0, and we get 100 to 27.53 kilopascal. And the second question is the pressure in, which is P in at the pipes. We also use the same equation from the first question, but the height we change to 8.25 meter, and we get 18.93 kilopascal. The third question is the velocity of the water when enter the pipes. We use the formula from the Bernoulli equation to find out the velocity when entering the pipes, and we get 12.7226 m per s. The fourth question is the flow rate, which is Q. Then we get 22.4827 m cube per s. The fifth question is the pressure out at the pipe, which is P up, and we use the Bernoulli equation and we find out the pressure up is 125.078 kilopascal. And the sixth question is we try to find out the major loss of the pipes and assume that we ignore the turbine. We separate into three parts. That is first that the leaning part when the water enter, then the horizontal part of the pipes, and the third part is the horizontal part of the pipes after bending, which is nearby the exit of the pipes. So first we find out the Renault number, which is RE, and we get 10905085.71, which is greater than 4000. It is turbulent flow, and we find the relative roughness. That then we find the F based on the Moody diagram. We get the 0.0027. Then we get the major loss. The total major loss is 189.1291 meter. The last question is the minor loss of the pipes. We assume we have the inlet loss, the two elbow loss, and the exit loss. And we assume when we calculate the inlet loss, we assume that it is a square edge inlet. Then we get 4.125 meter. When we calculate the elbow, we assume that it is the 90-degree standard elbow, and we get 0.6682 meter. And last is the exit. We assume that it is a square edge inlet also, and we get the same dimension with the inlet, which is 4.125 meter. And lastly, we get the total minor loss is 9.5864 meter. Thank you.
Good evening, everyone. My name is Chansing Yi, and my student ID number is RA24035. I would like to continue about the losses that may occur in a dam system. Losses may occur in a dam system due to various factors, which is major losses, minor losses, structural losses, and operational losses. First, major losses. Major losses can occur due to friction within a pipe. Friction loss refers to the measure of energy loss in a piping system due to resistance faced by fluids as they move through the pipes. The resistance can have significant impacts on efficiency. First, length of the pipe. Shorter pipe length can reduce the frictional loss. From the Darcy-Weisbach equation, frictional loss increases with the length of pipe. So, the longer the pipe, the higher the frictional loss. Next, diameter of pipe. Also from the Darcy-Weisbach equation, we know that frictional loss increases inversely with pipe diameter. This means that smaller diameter of the pipe will have higher change of friction loss due to the increase of the surface area of the pipe. Thirdly, interior pipe roughness. Smooth materials should be used as surface area of pipe to reduce the friction losses. This is because the closer the internal surface of the pipe, the harder the fluid needs to slide around them. Then, the higher the losses occur in the dam system. One of the key factors contributing to friction loss is fluid viscosity. Viscosity is a measure of fluid resistance to flow. It describes how thick or thin a fluid is. For example, honey, which has high viscosity than water. When a fluid has high viscosity, it tends to flow more slowly. The slower movement can lead to increase of friction loss. Flow condition can also occur losses in a dam system. Energy loss due to friction for two categories of flow in pipelines, which is laminar flow and turbulent flow. Darcy equation and Hagen-Poiseuille equation are used to show the energy loss due to friction. Usually, laminar flow has less frictional loss than turbulent flow due to high velocity near the surface. Now, let's discuss about the minor losses. Minor losses mean losses of pressure due to components in a piping system other than a straight section of the pipe. First, gradual enlargement or sudden enlargement. This is same with gradual contraction or sudden contraction. Energy loss because of turbulent flow. Thus, the smaller the angle of the enlargement or contraction, less the minor losses occur. Next, axial loss, which refers to the situation where pipe enters a tank which is a very large enlargement. The larger the angle of the bank of pipe, the larger the minor losses occur. Entrance loss have same theory with axial loss too. Fluid move from zero velocity in tank to second velocity. Sudden expansion or contraction at the pipe entrance or exit, there can be abrupt changes in diameter leading to losses. Besides that, with fitting and bend in pipe such as elbow, T, U-bend, cross, and wide fitting. Losses indirectly proportional to geometry of device of velocity. Structural losses. Structural losses means the losses occur due to physical damage such as cracking of pipe, corrosion of pipe, and overtopping. Cracking is usually used due to defective design and construction. Small leak in wall grew bigger and weaken the wall through piping. Then, dam wall may burst due to pressure of accumulated rain. Corrosion. Fluid that past the rusting surface area may be polluted and the viscosity of the fluid may be increased. As I mentioned at the beginning of the slide, the higher the fluid viscosity, the higher the losses in the dam system. Lastly, overtopping due to poor foundation quality. Heavy rain, excess wind, or overcrowded may cause dam collapse. Operational losses, which usually refers to inefficiency in the operational. For example, the operation of the dam gates, turbines, and machinery system. If these operations are not maintained properly, the efficiency in power generation of water management may reduce. In conclusion, understanding the losses may occur in a dam system is essential for those who involve in fluid transport system. By knowing the losses may occur, we can manage the losses to enhance the efficiency of piping system. So now, I'm going to talk about the proposal on how to reduce losses. First of all, regular maintenance and repairs. Water management should be occurred for cleaning purpose. This can avoid corrosion or semi-metal in the pipe system and ensure the cleanability of the fluid passed across. Thus, fluid viscosity can be reduced, frictional force can be reduced, and so on. The energy losses can also be reduced. Besides that, the regular checking of the operation in dam system should be occurred. This can help to identify the problems of dam systems such as cracking of dam and low power generation. Thus, the issue can be fixed as soon as possible and avoid any incident that may happen. Next, the enlargement or contraction of pipeline should be reduced with decreasing the angle of the enlargement or contraction of pipeline. For example, they can use radial enlargement or contraction of pipeline instead of sudden enlargement or contraction of pipelines if possible.
This can reduce the turbulent flow and friction losses.
Next, we use larger pipe diameter. Larger diameters have smaller surface area. Energy loss increase inversely to pipe diameter. The larger the diameter, the lower the resistance of the flow. So it makes the lower the energy loss. And next is the reduce the turns and bends in pipes. Increase the straightened part of the pipes can increase the flow of the fluids. We reduce the angle of bends of the pipes, so this can help to reduce the turbulent flow and energy loss. Next, we use smooth material for the interior pipe. Smooth surface has fewer irregulating parts. Stainless smooth surface can reduce the resistance and friction losses as fluid can move over it more quickly and easily. We can also use shorter pipe length. According to the formula, friction loss increases with the length of pipe. Shorter pipe length has a small surface area which can reduce the loss of energy. Next, we use permanent magnet generators because it does not require external excitation, hence reducing the energy loss.
Hi, my name is Kavisha Selvam, student ID RA24041, and I will be concluding this work-based project. In summary, this work-based project has achieved all of its objectives, which were understanding the fluid mechanics principle, identifying the parameters and characteristics of the dam system, calculating the flow of the dam system, examining the losses that may occur in the dam system, identifying ways to reduce the energy losses in the dam system, and practical applications in engineering field. Application of fluid mechanics principles in the dam system includes Bernoulli's equation, flow patterns, Darcy's equation, Reynolds number, loss coefficients, and resistance coefficients. The parameters and characteristics of the dam system are penstock, granite bedrock, Kaplan turbine generators, depth and thickness of the wall, arc shape of the wall, intake tower and generator turbine house. Calculations involved in the flow of the dam system includes pressure at the base of the dam, pressure in the pipes, velocity in the pipes, volume of flow rate, pressure out of the pipes, Reynolds number, total major loss in the pipes, and total minor loss in the pipe. The pressure at the base of the dam equals to 127.53 kilopascal. The pressure in the pipe equals to 80.93 kilopascal. The velocity in the pipes equals to 12.72 meter per second. The volume of flow rate equals to 22.478 meter cube per second. The pressure out of the pipes equals to 125.078 kilopascal. Reynolds number equals to 10902.857.14. Since Reynolds number is more than 4000, the flow is turbulent flow. Total major loss in the pipes equals to 189.052 meter. And last but not least, total minor losses in the pipes equals to 9.582 meter. Not only that, the losses that may occur in the dam system can be divided into four main categories such as minor losses, major losses, structural losses, and operational losses. Last but not least, ways to reduce the energy losses in the dam system includes regular maintenance and repairs, use larger pipe diameter, use smooth material for the interior pipe, use shorter pipe length, reduce the turns and bends in pipe, reduce the enlargement or contraction of pipelines, and use permanent magnet generators. Thus, the dam system is a good example of a real application of fluid mechanics. That is all from Group 2. Thank you.